Okay, so in this video I'm going to be working through the VCAA 2016 Exam 1 for Mathematical Methods. As you should be aware, this is a 1-hour paper with 15 minutes of reading time. It's completed without reference to your BAM reference and with no calculators, CAS or otherwise. Yeah, so let's get started. Make sure you're aware of the instructions that appear on the cover. Every year the VCAA releases the cover sheets ahead of the exam, so make sure that you're fully aware of that. For example, last year in 2019 was the first time that they specified that you must complete Exam 1 using a blue or black pen. That's because they have started scanning the methods papers, where in the past markers have marked physical papers. Now they're being scanned. They want to make sure that you're writing in a blue or black pen so it remains legible when it is scanned. So that would be a change to the instructions that appeared in 2019 that hadn't appeared on the cover before then. So making sure that you're aware of all these instructions before you even start. And then there are some other important instructions that are actually inside the booklet. So usually on the first page of questions, there are some instructions which, again, these haven't changed for many, many years now. But it's essential that you are aware of these. In fact, if you are not aware of these before now, you've been in trouble in your SACs and other assessments. In questions where a numerical answer is required, an exact value must be given unless otherwise specified. So you do not give a rounded decimal value unless the question tells you to give an answer to 2 decimal places, for example. That's less of an issue in Exam 1, where we haven't got a calculator anyway, but certainly worth being aware of, particularly in Exam 2. The second important information here that's always referred to in the examiner's reports every year is that in questions where more than 1 mark is available, appropriate working must be shown. So as you work through the paper, part of your technique has got to be to also be aware of how many marks the question is worth. That indicates to you how much work you need to do, what you need to be showing. Start to get good at thinking about, okay, what am I going to earn those 2 marks for? In Maths Methods, if you simply write an answer, regardless of whether it's correct, if the question is worth more than 1 mark, you will not earn more than 1 mark for your correct answer. Okay, so you must have appropriate working if the question is worth more than 1 mark. Okay, let's get on with the questions. Question 1. If you've done some practice exams prior to now, you'll know that Exam 1 always begins in the same way. It's usually a 2-part differentiation question using a combination of product, chain and or quotient rules. And one of them you'll just calculate a derivative, the other you'll need to actually evaluate that derivative at a particular point. And this year, 2016, is no different. Okay, so we want to let y equal cos of x divided by x squared plus 2, and we want to find dy dx. So this is a quotient of a cos function and a quadratic function, and so we're going to use the quotient rule to differentiate here. It is possible to avoid using the quotient rule by instead using product and chain rules. So if you were to rewrite this as cos of x times x plus 2 to the power of -1, you could use the product rule and a chain rule. Okay. However, and I used to advocate that, however, you've got the quotient rule on the formula sheet, so there's no excuse for remembering it incorrectly, and I genuinely think that the expression that you end up with after you've done the quotient rule is a more manageable expression if you then need to go on and do things with the derivative. So I tend to advocate quotient rule. As I said, be aware of your formula sheet and what's available to you on the formula sheet. Here is your quotient rule here, so you can make sure that you're getting that subtraction around the right way. There's absolutely no reason for getting things like that wrong, so please be aware of what's on your formula sheet and reference it as needed. Okay, so dy dx, we're going to use the quotient rule, so derivative of the numerator, derivative of cos is negative sine x. Once again, if we need it, derivative of cos is here on the formula sheet. So derivative of cos is going to be negative sine x. Multiplied by, we leave the denominator as it is, subtract, leave cos as it is, and multiplied by the derivative of the denominator, which is 2x, all over the denominator squared. Now, one of the things they frequently say in examiners' reports is don't do more than you have to, basically. Sorry, I'm just going to write that quadratic at the front of the sign. And an example of where you might do unnecessary work would be in attempting to, if you chose to attempt to expand out that denominator, there's absolutely no reason to expand it. Expanded or factorized forms, neither is more simple than the other. It is just a different way of writing the same thing. So you're gaining nothing by expanding the denominator. In fact, you're running the risk of making a mistake when you do that and taking what was a perfectly correct derivative and turning it into something that is no longer correct. So please, minimum, do what you need to do to answer the question and you're done. In fact, you could probably stop at this point. I just like to write it without the multiplications and to put the coefficients and things at the front. But, as I said, there'd be 2 marks earned here. The 2 marks in a question like this are for recognising and attempting to use the quotient rule or the product and chain rules, if that's the way you chose to do it. And then obviously the second mark is for obtaining the correct answer via that. So a method mark for recognising the quotient rule is needed. Now that you would probably still earn the mark for the quotient rule, even if you make mistakes in some of your derivatives or whatever. It's a sense that I can see that the student knows that they need to use a quotient rule here, and then in having executed it correctly, you'll earn the second mark. Part B, f of x is x squared times e to the 5x, so it's going to require a product rule to differentiate. Again, you've got your product rule on the formula sheet. I personally tend to remember it the other way around, v times du dx plus u times dv dx. That is the derivative of the derivative of the first function times the second plus the first function times the derivative of the second. Only because that way you actually get you're doing things in the same order as you do them for the quotient rule. It's a plus instead of a minus. So I tend to remember the product rule in a particular way. I find it helps with remembering the quotient rule. Okay, so derivative f dash x, as I said, I do derivative of the first function, so derivative of x squared is 2x, and I leave the second function as it is, plus leave the first function as it is, derivative of the second function, which is 5e to the 5x. Once again, derivative of e to the power of x is on your formula sheet. No excuses for making mistakes with these things when you're given those rules. Okay, we could do whatever we want here. There is some factorising that could be done here, but what you're going to substitute a number in into this expression anyway, so there's absolutely no need to factorise out. Yes, there's a common factor of x times e to the 5x, you could do that, but you're going to substitute 1 in anyway, so it really doesn't matter how much work you do with that. I probably didn't even need to write that second line. So f dash at 1 is 2 times 1, so 2e to the 5 times 1, so 2e to the 5 plus 5 times 1 e to the 5. So 2 lots of e to the power of 5 plus 5 lots of e to the power of 5 are 7 lots of e to the power of 5. Okay, question 2. You've got a square root function here. It's got a domain that isn't R, but that's not a restricted domain, that's just the implied domain for the square root function. So we want to find the derivative of f. So, I want to think first of all about rewriting f in a form so that it's ready to be differentiated. So it is 1 minus 2x to the power of a half. So that's going to require the chain rule. So in the first 3 parts here, we've used product, chain, and quotient rules. You can certainly expect to be assessed on those 3 rules at some point through exam 1. Okay, so chain rule, I don't tend to use the rule for the chain rule on the formula sheet because I tend to think about it slightly differently. I think about it as a derivative of the outside function times the derivative of the inside. So here I've got something to the power of a half. The derivative of that is half times that something to the power of negative a half. And then I multiply by the derivative of the inside function, so the derivative of 1 minus 2x, which is negative 2. Half times negative 2 is negative 1. You might also choose to write that back with the square root. In terms of earning the mark here, either of these answers would be sufficient in having differentiated. I would say at this point you should definitely be multiplying those numbers together. That's not really sufficient. Okay, part B. Find the angle, theta, from the positive direction of the x-axis to the tangent of the graph of f at x equals negative 1, measured in the anti-clockwise direction. Okay, there's quite a lot of information there, so you've got to work your way through. So we're ultimately trying to find an angle theta. Our final answer is going to be theta equals something. Try to think that through when you're doing a question. What is my answer going to be? You don't want to be ambiguous about having answered the question. Somewhere towards the end of my working here, it should say theta equals something. And that's what I need to do. Okay, so it's an angle from the positive direction of the x-axis to the tangent. Okay, so let's just get a bit of a sense of what's happening. So you've got some kind of tangent. You've got positive direction of the x-axis, the tangent. in an anti-clockwise direction from the positive direction of the x-axis to the tangent, we want to find that angle. So that's essentially what we're trying to find here. So the first thing we're going to need is we're going to need the tangent. In particular, we don't actually need the equation of the tangent. The only thing we're really interested in is the gradient of the tangent. Because let's remember, sorry, we should have been clear. Let's remember that if you've got a line and you're trying to find this angle in here, okay, this is the rise and this is the run. And we know that gradient is rise over run. But this is, if we think about that relative to that angle theta, this is the opposite side and this is the adjacent side. And so therefore the gradient is also equal to opposite over adjacent, which is tan of theta. Okay, so we remember this property that tan of theta is equal to the gradient. So that's what we're going to need to utilize in this question. So we really need to find what the gradient of that tangent is. Okay, so the gradient of the tangent to the graph of f at the point x equals -1. So we want to know what the derivative is at -1. That will give us the gradient of our tangent is the derivative at -1. So that is -1 over square root of 1 minus 2 times -1. So it's -1 over square root of, that's 1 plus 2, so square root of 3. Okay, so actually we've got a negative gradient here. Okay. So we've got a gradient of -1 on root 3. We still want the angle from the positive x-axis in an anti-clockwise direction around to the tangent. So we're still trying to find that angle. So I'm expecting it to be an angle bigger than 90 degrees. So just sort of thinking through that logic as well. Okay, let's think. We know then that tan of theta is equal to the gradient of the tangent. So that is that tan of theta is equal to -1 on root 3. We're therefore going to need our exact values. So I remember my exact values by using my special triangles. So this is going to come from the triangle that is half an equilateral triangle. Okay, half an equilateral triangle, you can make it any side length, but side length of 2 makes the numbers simplest. So if I want tan to be 1 over 3, that means the 1 needs to be the opposite side and the 3 needs to be the adjacent side, and so therefore we must be talking about the angle up the top here, which is half of a 60-degree angle, so 30 degrees. Now, degrees is not the default angle measure, so the default angle measure is radians. So if it wanted the answer in degrees, it would need to say theta degrees, but it just says theta, and so we're going to stick with radians. So 30 degrees in radians is pi on 6. So we know that tan of pi on 6 is 1 on root 3. So obviously tan has to be -1 on root 3. So tan is negative in these two quadrants. Pi on 6 up from there, pi on 6 down from there. And so it's therefore going to be, this is the angle that we're after given the diagram we want. So that's pi minus pi on 6, which is 5 pi on 6. So theta is going to be equal to 5 pi on 6. Yeah, and don't be ambiguous about your answer. Consider sort of underlining or putting a box around your answer. You can use a highlighter, although now that they're scanning the papers, a yellow highlighter, unless they scan in colour, a yellow highlighter doesn't actually show up when you scan or photocopy. That's one of its benefits, but yeah, so that might not be the best option anymore. I'd think about underlining or drawing a box around it. Although if they're scanning colour, it wouldn't be an issue, so I'm not really sure. Okay, question 3. Let f be this hyperbola. The domain is r excluding 1. Again, that's not a restricted domain. That is the implied domain of this function. Some students find it easier to think about this as being 3 over x minus 1 plus 2, so same thing. So we've got a dilation of the hyperbola by a factor of 3 from the x-axis. Doesn't change how you draw it, particularly when you calculate your intercepts. That'll come into account then. The minus 1 under here is a translation to the right by 1, and the plus 2 here is a translation up by 2. So the right 1 and up 2 are the most important things in the sketch. In terms of, we need to draw those first to draw in the asymptotes. So right by 1 means the vertical asymptote is at x equals 1. That's also reinforced by the domain being r excluding 1. The question specifies that you need to label any asymptotes with the appropriate equation. So x equals 1 is the vertical asymptote. Okay. Even if it didn't say that instruction, that's implied. drawing a graph with asymptotes, you need to label the asymptotes with equations. The vertical asymptote, we've gone up by 2, so that is at y equals 2. So we've got our asymptotes drawn in and labelled with equations. Now, the VCAA didn't used to give grids quite so often, or fully scaled axes, and I actually think it requires more accuracy of you when you have a grid. Because I can't just draw this bit in up here like this, because what if it's meant to go through this point and this point and this point? Then it's actually not the right graph. So you do actually need to calculate more things when the grid is here to make sure that you're going through the right sort of points on the scale. So we're obviously going to also have a branch down here. We're going to have x and y intercepts happening somewhere in this region, so we need to calculate those as well. So let's do that. Let's do our y-intercept is going to be f of 0. So that's 3 over negative 1 plus 2, which is negative 3 plus 2, so negative 1. So our y-intercept at 0, negative 1. Label the axis intercepts with their coordinates. VCAA always asks for coordinates. Please get in the habit of always labelling graphs with coordinates. I teach my Year 9 and 10 students to always label graphs with coordinates. You establish the habits back then, you don't even have to think about it when you get to VCE, when the VCAA always asks for coordinates. Okay, the x-intercept, let's let y equal 0. Okay, so that's going to be 3 on x minus 1 equals negative 2. Now you could, so 3 equals negative 2x plus 2, so I did the expanding out as I multiplied. So 1 equals negative 2x, and therefore x is going to be negative 1/2. Okay, so that means the x-intercept is at negative 1/2, 0. Okay, so negative 1/2, 0 for my x-intercept is there, 0, negative 1 for my y-intercept. I'll label them with coordinates once I've drawn the graph in. Now, as I said, I'm going to calculate some other values. So, for example, I'm going to look at when x equals 1/2 to just get that in the right place. So, when x equals 1/2, y is going to be 1, sorry, not 1 over. It's going to be 3 over negative 1/2 plus 2, which is negative 6 plus 2, which is negative 4. Okay, so I'm going to go through that point there. When x equals negative 1, it's going to be y equals 3 over negative 1 minus 1, negative 2 plus 2, so it's negative 1.5 plus 2, so that's positive 1/2. When x equals negative 2, y is going to be 3 on negative 3 plus 2, so that's negative 1 plus 2, which is 1. When x equals negative 3, it's going to be 3 on negative 4 plus 2, so it's negative 3/4 plus 2, so that's going to be positive 1.25. And when x equals negative 4, 3 on negative 5 plus 2, so that's 2 minus 3/5, so it's 1 2/5, so it's just going to be a bit bigger than that. Okay. And again, over on the right-hand side, we're going to have when x equals 2, for example, it'll be y equals 3 on 2 minus 1 plus 2, so that is 3 plus 2, which is 5, so it goes through 2, 5. When x equals 3, y equals 3 over, that'll be 2 plus 2, so 1.5 plus 2 is 3.5, so 3.5. When x equals 4, it'll be 3 on 3 plus 2, so it's 1 plus 2, so that's 3. Okay, maybe when x equals 1.5, so 1.5 minus 1 is 1/2, so 3 divided by 1/2 plus 2, so that's 6 plus 2, which is 8, so that's way off the scale. Okay, so when x equals 1/2, it's going to be at 8, which is somewhere right up here. Okay, so thinking about that, your graph shouldn't be crossing over here, it should be meeting the edge here, sort of. Okay, so joining the dots with a smooth curve. The scale here actually means that your graph doesn't get particularly close to that asymptote at all, which helps with trying to draw the asymptotic behaviour correctly. I've marked VCAA exams once in 2012. Life got busy after that and I haven't done it since then, but I do remember at that time, I'm pretty sure it was a hyperbola or it might have been a truncus in that year. And they were very, very, very particular. It was in the Tech Active exam, but very particular about shape. It's really important that you draw that correctly. So usually in the past, I would have said always draw graphs with pencil. I would have encouraged you to complete the exam in pencil, but the changes last year mean that you now have to complete the exam in a blue or a black pen for the scanning purposes, but I would still advocate draw the graph in pencil until you're comfortable that you've got the shape right, and then go over it with a pen. Okay, graph shape is really important. Graphs are a really easy point to earn good marks, but also an easy place to lose marks. So you've got 3 marks there. I would suggest 1 is for the asymptotes, correctly drawn and correctly labelled with equations. 1 would be for your x and y intercepts, and 1 would be for the shape of your graph. Sorry, I haven't quite finished. I haven't labelled my intercepts with intercepts with coordinates. So -1/2, 0 for that intercept, and 0, -1. Okay, so we're done. Find the area enclosed by the graph of f, the lines x equals 2, x equals 4, and the x-axis. Okay, so let's have a look at our graph. So x equals 2 is this line, x equals 4 is this line, x-axis is this line, curve is this line. Oops. Sorry, it should be up there. And so we're looking at finding this area. So it's a simple integral. Everything's above the x-axis. No need to break it into separate regions. So the area in this case is going to be the integral from 2 to 4 of f of x with respect to x. Okay, so that is 2 plus 3 over x minus 1. Okay, so the antiderivative of 2 is 2x. The antiderivative of 3 over x minus 1 is the same as 3 times the antiderivative of 1 on x minus 1. And that is going to be log e of, technically, the modulus of x minus 1, but given that we're going to substitute 2 and 4 into that modulus, 4 minus 1 is a positive number, and 2 minus 1 is also a positive number, so there's no issue there. So if you write round brackets, there's no problem with that. So let's substitute in. 2 times 4 is 8, plus we're going to have 3 times log e of 4 minus 1, which is 3. As I said, the modulus of 3 is 3, so we actually don't need the modulus signs, which are those vertical lines. We can just write it with round brackets. Subbing in 2, so 2 times 2 is 4, plus 3 times log e of 2 minus 1, which is 1. Again, absolute value or modulus of 1 is just 1, so we don't need the square brackets. Log e of 1 is 0. Okay, so we're going to have 8 plus 3 times log e of 3 minus 4 and then minus 0, so no worries there. So that is 4 plus 3 log e of 3, and it's an area, so that is in square units. Okay, question 4. A paddock contains 10 tagged sheep and 20 untagged sheep. 4 times each day, 1 sheep is selected at random from the paddock, placed in an observation area and studied, and then returned to the paddock. What is the probability that the number of tagged sheep selected on a given day is 0? Okay, so you're selecting 4 sheep and you want to know what's the probability that they are all 4 of them untagged sheep. So you really don't need anything too complicated here. If you sort of imagine the tree diagram, you're going to have 4 sets of branches, tagged, 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 untagged, untagged, etc. Okay, so all you're interested in here is the probability that the 4 sheep you select are untagged. So the probability of getting 1 untagged sheep is 10 out of 30, which is a third. And so it's simply going to be a third times a third times a third times a third. Okay. So it should just be, oh, sorry, no, the probability of being untagged is 2/3. So the probability of being tagged is a third, and the probability of being untagged is 2/3. So it should be 2/3 times 2/3 times 2/3 times 2/3. Okay. So if you think it through that way, it's easy enough to say, the probability of no tagged sheep is just going to be 2/3 to the power of 4. 2 to the power of 4 is 16, and 3 to the power of 4 is 81. You can also set it up as a binomial distribution, okay? If it was, t is the number of tagged sheep selected, and t is a binomial distribution. You're selecting 4 sheep. The probability of 1 being tagged is a third, and you want the probability that t equals 0. That is going to be 4 choose 0, 1/3 to the power of 0, and 2/3 to the power of 4, which is just 2/3 to the power of 4, so 16 on 81. Okay, but really it doesn't really need the binomial distribution. What is the probability that at least 1 tagged sheep is selected on a given day? So probability of at least 1 tagged is equal to 1 minus the probability that you've got no tagged sheep. So it's simply 1 minus 16 on 81. 1 is 81 on 81. 81 minus 16 is 65 on 81. Okay, these are just 1 mark questions, so just 1 mark for your answer would be all you're getting there. And then what is the probability that no tagged sheep are selected on each of 6 consecutive days? Okay, so we know in part A we've found the probability that we get no tagged sheep on one day, and so if that happens for 6 consecutive days, it would be that to the power of 6. Okay. Express your answer in the form a over b all to the power of c, where a, b and c are positive integers. We have a, b and c as positive integers in this particular answer, and we've written our answer in this particular form. So what they're telling you there is that you don't need to work out what 16 to the power of 6 is, nor what 81 to the power of 6 is. The question is not asking you to find a, b and c, so your answer shouldn't be a equals something, b equals something and c equals something. The question is asking you to express your answer in this form, and that's what we've done. Okay, question 5. Let f be a log function. Again, that's not a restricted domain, that's just the implied domain of log e of x, so positive real numbers. And g of x be a quadratic function. Again, no domain restriction there. Find the rule for h, where h of x equals f of g of x. Okay, so it's only a 1 mark question, so we're assuming that f of g of x exists, so there's not really enough marks that it's asking you to check that it exists before you actually find it. But if you think about g of x is a quadratic function up by 1, so we know that the domain of g is r and that the range of g is 1 to infinity. Log e of x is an unrestricted log function. The domain of f is r plus or 0 to infinity, and the range of f is r. If you want to do the composition f of g of x, you need the range of g to be a subset of the domain of f, which indeed it is. 1 to infinity is a subset of 0 to infinity. And so the composition exists. As I said, it didn't actually ask you to verify or to check that it does exist, and for only a 1 mark question, the mark is just for finding the rule, so you don't really need to do that. Okay, so h of x is f of g of x, so we're going to take g of x, which is that, and we're going to substitute it in place of x in f of x. So we're going to have f of x squared plus 1, which means we have log e of x squared plus 1 is h of x. Just asks for the rule, so it's not asking you for the domain. If it asked you for the function h, implied in a function is both rule and domain, but that's why it specifies just the rule. Part 2 is asking us about the domain and range of h. Okay, so the domain of a composite function is quite straightforward. The domain of h is equal to the domain of the inside function, so in this case that's the domain of g, and we can get that from the question, that's just r. Now, the range of h, however, we have to think a bit about what's actually happening in this particular composition. Okay, so what happens is we're taking x values initially, okay, and where x can be any real number, and we're putting it into the rule for g, and the rule for g is that we square it and we add 1 to it. So the numbers that come out of that are going to be the range of g, which is just, we've already talked about, is from 1 to infinity. Those are the numbers that then go into f. Okay, so that essentially becomes the domain for f, and the rule for f is log e of x. So what we want to think about for the range of h, which is what comes out at the end here, is going to be essentially the range of log e of x over when the domain is 1 to infinity. Okay, so log e of x looks like this. That's the 0.10. So if it's only got a domain from 1 to infinity, its range is only from 0 to infinity, inclusive of 0. And so the range of h is 0 to infinity. Either that, or you need to actually know what the graph of log e of x squared plus 1 looks like, and think about what the range would be over the given domain. Okay, show that h of x plus h of negative x is equal to f of g of x all squared. Okay, so show that question, it's really important that you do these properly. We cannot assume that these two things are equal, okay? So you don't just substitute the functions in for the left and the right hand side at the same time and then manipulate it. What you end up with is a meaningless statement at the end that essentially says that 0 equals 0 or 1 equals 1 or 10 equals 10, which is useless. We all know that. What you need to do is you need to start with the left hand side of the function and manipulate it until you can show that it's equal to the right hand side. Or start with the right hand side and manipulate it until you can show it is equal to the left hand side. You don't assume that they're equal from the start. Now, generally speaking, I would say you go from, it's usually easier to go from the more complicated thing to the neater looking thing. This looks more complicated, but it's actually not that complicated an expression, but you can do it either way. I'm going to start with the left hand side and turn it into the right hand side. So I'm going to start with h of x plus h of negative x. Okay, so h of x we've got written up here in part 1. H of x is log e of x squared plus 1 plus log e of, so we want h of negative x. Now again, I know that most of you probably know that negative x all squared is positive x squared, but you're trying to show that, okay? So be clear about the fact that this is what h of negative x is, but yes, that's going to be equal to log e of x squared plus 1. Fine. When you're doing a show that, you don't want to skip steps, okay? You're trying to demonstrate clearly without any ambiguity that you know how to get from here to here, okay? Alright, so we've actually just got log e of x squared plus 1 plus log e of x squared plus 1. So we've actually got two lots of log e of x squared plus 1. And then log laws tell us that we can move that 2 up into the power. And so that is log e of x squared plus 1 all squared, which is log e of g of x squared, which is therefore f of g of x squared. And so we have shown that that is true. The same, you can work your way back the other way as well, in reverse. It works both ways. Part 2, find the coordinates of the stationary point of h. So it specifies there's only one and state its nature. Okay, so for stationary points we want the derivative equal to 0. So the derivative of h of x. H of x is log e of x squared plus 1. In fact, I'm just going to write h of x down here so I can see it. Okay, so the derivative of that requires a chain rule. We've got log of something, 1 on that something is the derivative, plus the derivative of the something, so derivative of x squared plus 1, sorry, not plus, times, derivative of x squared plus 1, which is 2x. Okay, so we've got 2x on x squared plus 1. Okay, so we then want to solve that equal to 0 for the stationary points. The only way that a fraction is equal to 0 is if the numerator equals 0, and so that means that x must equal 0. We want the coordinates of the point, so let's substitute that back into the original function. So that is log e of 0 squared plus 1, log e of 1 is 0. Okay, so we know we've got a stationary point. Stationary point at 0, 0, but we don't know what kind of stationary point it is. Now, I don't know what the graph of log e of x squared plus 1 looks like, personally. I could probably work it out, but I don't need to do that. I'm going to utilise a sign diagram to show the nature of the stationary point. So that is to consider the gradient at either side of the stationary point. Okay, so I'm going to do, I probably don't need that, I'm going to do x equals, I'm going to then calculate the derivative at those x values, and I'm going to interpret what that means for the shape of the graph. Okay, so we know when x equals 0, the derivative is 0, that means we've got a stationary point at that point, so the gradient is flat. Okay, let's have a look at either side of that point. Now you want to stick pretty close to 0, but we actually know that this is actually the only stationary point. That was the only solution to the derivative equal to 0, so we can actually go as far as we want away from 0 because it doesn't ever turn again. So, but I'm going to work out what h dash at negative 1 is. Okay, so that's substituting into my derivative here. So subbing negative 1 in here to my derivative. So that's going to be negative 2 over positive 2. So that's going to be negative 1, the derivative. And then substituting positive 1 into the derivative. 2 times 1 is 2 on the numerator. 1 squared plus 1 is 2 on the denominator. 2 on 2 is 1. So we've got negative gradient, zero gradient, positive gradient, okay? And so therefore, 0, 0 is a local minimum turning point. Now, it's actually not a local minimum. We actually know that it is an absolute minimum. But I think as long as you refer to minimum, it will be okay. And it's an absolute minimum because it's the only turning point. So we know that it's a minimum turning point, but given that it's the only point where the graph turns, if it only ever turns at 0, 0, okay, it's not a parabola, but whatever it looks like, I don't know. If that's the only point that it turns and it's a minimum point, it means the whole graph is going to always be above there because it can't ever turn around and come back again. So it is not just a local turning point, it's an absolute minimum turning point. Okay, so let K be, okay, so it's got the same rule as h of x, but it's got a restricted domain now, so only from negative infinity to 0. So thinking about, we're now only interested in the left-hand half of this up to the turning point, and that's about ensuring that it's a one-to-one function so that we can then find the inverse function, which is what this question is asking us to do. Okay, so to find the inverse function, you need to swap x and y, and I do that by letting k of y equal x. Okay, and so that means it is log e of y squared plus 1 equal to x. Y squared plus 1 equals e to the x. Y squared equals e to the x minus 1. And then therefore y is positive or negative square root of e to the x minus 1. Okay, so then we need to decide for the inverse function, is it the positive square root or the negative square root? And it's a bit to do with the range and also thinking about what the original graph looks like. But I might think about the fact that the range of the inverse is the domain of the original, which we know is negative infinity to 0. So it's going to have negative y values, which means that we're going to want the negative square root. Okay, and so therefore the inverse function of k is only the negative square root. There's a lot that's important about notation when you're finding an inverse function. Be really careful about that you don't ever just go straight from the line y equals log e of x squared plus 1 to the line x equals log e of y squared plus 1, because there's no mathematical logical statement that takes you from there to there. These aren't equivalent equations. These are whole different equations. So there needs to actually be something in the middle there, like let swap x and y. You actually have to write that if you want to, if you're going to write those two lines. I avoid that by not writing the first line in the first place. I go straight to swapping x and y by saying let k of y equals x. It also means I've introduced y into the problem. There actually isn't y otherwise. So normally I would say that you have to say let y equal log e of x squared plus 1, swap x and y for the inverse, and then so you've got x equals y squared log e of y squared plus 1, and then you can go on and solve it. I find this ties those together neatly. The other thing is to make sure that you've actually answered the question, which is to find a rule for the inverse of k, and so you actually need to state the inverse of k. It's not just y equals. Okay, so making sure you've answered the question. State the domain and range of inverse of k. Okay, so the domain of the inverse of k is the range of k. Okay, and again, thinking about the fact that we know k is the same as h, and it has just the one turning point at 0, 0, and it's a minimum turning point. The range, even when we restrict from negative infinity to 0, the range is clearly 0 to infinity. So that becomes the domain of the inverse function. And then the range of the inverse function, I've already stated in part 1, is the domain of the original function, which we're given in the question. So this is a gift of a mark, negative infinity to 0. Okay. Okay, question 6. Let f be this trig function with a restricted domain from negative pi to pi. Calculate the average rate of change of f, and if you look ahead, B asks for the average value of f. So this was a really clear test of something that they know that students confuse all the time. Can you be clear about what is the difference between average rate of change versus average value? So average rate of change has got nothing to do with derivative, even though rate of change is about gradient and derivative. Average rate of change is simply the change in the y values over the change in the x values. So that is f at pi on 6, so the y value at pi on 6, minus f at negative pi on 3, so the y value at negative pi on 3, over pi on 6 minus negative pi on 3. Okay, let's work out some of those values before we go here. So f of pi on 6 is going to be 2 times sine of 2 pi on 6, which is pi on 3, take away 1. Okay, I need my exact values again. I think about my half an equilateral triangle of side length 2. That makes this a 60-degree angle, which is pi on 3. That's what I'm interested in. Halving it makes that 1. Using Pythagoras tells me that's root 3. Sine of pi on 3 is the opposite over the hypotenuse, so root 3 on 2. So it's 2 times root 3 on 2, take away 1, so it's going to be root 3 minus 1. And then f at negative pi on 3 is 2 times sine of negative 2 pi on 3, take away 1. Okay, so negative 2 pi on 3, alright, we know that sine of pi on 3 is the y coordinate up here, and it's root 3 on 2. So negative 2 pi on 3 is around here, so its y coordinate is going to be negative root 3 on 2. Okay, so this is 2 times negative root 3 on 2, take away 1, which is negative root 3 minus 1. Okay, let's put those in. So we're going to have f of pi on 6 is root 3 minus 1, take away f at negative pi on 3, which is negative root 3 minus 1, all over, that is pi on 6 plus pi on 3. Okay, so we've got root 3 minus 1 plus root 3 plus 1 over, let's get a common denominator there, pi on 6 plus pi on 3 is 2 pi on 6, so that's 3 pi on 6, which is pi on 2. Okay, so we've got two lots of root 3, and the ones have cancelled out. We're dividing it by pi on 2, so that is timesing by 2 on pi. And so we're going to have 4 root 3 on pi. Okay, and then calculate the average value of f over the interval. So the average value is 1 over b minus a, so that's pi on 6 minus pi on 3, times the integral from a to b, so integral from negative pi on 3 to pi on 6 of our function, which is 2 sine 2x minus 1. Okay, so we just need to evaluate that. We've already worked out from the previous question that pi on 6 minus pi on 3 is pi on 2, and so 1 divided by pi on 2 is 2 on pi. Then I'm going to do the antiderivative. Antiderivative of sine 2x, again, your rules are on your formula sheet, so we can check over here. So antiderivative of sine is negative cos, okay, and we need to divide by that a value. So it's going to be negative 1/2 cos of 2x, so that means we're going to have negative 1 because there's already a half there, cos of 2x, and antiderivative of 1 is x, and we're doing that from negative pi on 3 to pi on 6. Okay, so let's do some substitutions. So we're going to have negative cos of 2 pi on 6, which is pi on 3, minus pi on 6, take away negative cos of negative 2 pi on 3, minus pi on 3, so plus pi on 3. There's just lots of places that you can go wrong in these sorts of questions, so try not to skip steps, just work your way through it methodically. Okay. So 2 on pi. Now cos of pi on 3, let's go back up to the triangle I had up here. Cos of pi on 3 is adjacent over hypotenuse. So the adjacent side is 1, so it's 1 over 2. Okay, so that's negative half minus pi on 6. And then we've got minus. Now negative cos of negative 2 pi on 3. Now cos at negative 2 pi on 3 is the x coordinate, it's also negative. So it's the negative of cos of pi on 3, so negative half. So this is negative half, so it's going to be positive half. And then we've got plus pi on 3. Okay, getting there. 2 on pi. So in here we've got negative half minus pi on 6 minus half minus pi on 3. Okay, so that is 2 on pi, negative half minus a half is negative 1. Pi on 6, remember pi on 3 is 2 pi on 6, so you've got negative 1 pi on 6, take away 2 pi on 6, so that's minus 3 pi on 6, or minus pi on 2. Right, and then if we expand out the bracket, that's going to give us negative 2 on pi, and then 2 on pi times pi on 2 is 1, so that's minus 1. So that's our average value. Okay, question 7. Oh, sorry. A company produces motors for refrigerators. There are 2 assembly lines, line A and line B. 5% of the motors assembled on line A are faulty, and 8% of the motors assembled on line B are faulty. In 1 hour, 40 motors are produced from line A and 50 motors are produced from line B. At the end of an hour, 1 motor is selected at random from all the motors that have been produced during that hour. What is the probability that the selected motor is faulty? Express your answer in the form 1 on B, where B is a positive integer. Okay, so we can think about this in a couple of different ways. I'm going to think about it as a sort of tree diagram, because the first thing that happens is the motor is either made on line A or line B, and then it is either faulty or okay. Okay, so we know that 5% of the motors on line A are faulty. Now, I want my final answer as a fraction, so I'm going to leave this as a fraction. I'm just going to leave it as 5 on 100. I know that simplifies to 1 on 20, but just so that I've got the same denominators when in my maths, it's going to be a bit easier, which means it's 95 out of 100 are good. 8% of the motors on line B are faulty, so it's 8 out of 100 and 92 out of 100. Now we know that in the hour, 40 motors are produced from line A and 50 from line B, so that means the probability of choosing a motor from line A after that hour is 40 out of 90, so 4 nights versus 5 nights for line B. Okay, so we want the probability of a faulty motor. There are 2 ways for the motor to be faulty. It can come from line A and be faulty, or it can come from line B and be faulty. Okay, so line A and faulty is going to be 4 nights times 5 on 100, plus line B and faulty is 5 nights times 8 on 100, which means I've got 20 on 900. So see, by not simplifying the denominators in the tree diagram, I've still got everything over the same denominator of 900. 5 eighths are 40, so I've got 40 on 900, which means I've got 60 on 900, which is 6 on 9, which divided by 3 is 2 on 30, which is 1 on 15. There is my probability in the form 1 on B, where B is a positive integer. So B is 15, but it's not asking me to find B, it's asking me to express my answer in the form 1 on B. Part B, the selected motor is found to be faulty. What is the probability that it was assembled on line A? Express your answer in the form 1 on C, where C is a positive integer. Okay, this is a conditional probability. Given that the motor is faulty, what is the probability it came from line A? Okay, so this is probability of line A given that the motor was faulty. Now, conditional probabilities, again, it's a formula that's on your sheet. So conditional probability up here, A given B, it's A intersection B over B. Okay, so this is going to be the probability of line A and faulty over the probability of a faulty motor, which we've already worked out in part A. Okay, so line A and faulty is 4 nights times 5 on 100 over probability of faulty, we've already worked out, is 1/15. Okay, so 4 nights times 5 on 100 is 20 on 900, and we are dividing that by 1 on 15, which means that this is 2 on 90 or 1 on 45 times by 15 over 1, so it's 15 on 45, which is 1 on 3. That is in the form 1 over C, where C is a positive integer. Okay, question 8. I think this is the final question. Yeah, it's a number of parts, but it's the last question. Okay, so for those of you in 2020, this is a continuous random variable, so this question isn't applicable to the syllabus that you've covered in 2020, but if you are watching this in another year, I'm going to complete the question anyway. Also, even if you are in 2020, some of the maths of being able to do the integrals, part A you should be able to do, it's not connected to the continuous random variables. Part B, you just need a basic understanding of how to set up the integral, but then there's some good maths in actually doing that integral. It would be good for you to potentially practice that. And the last part here requires you to use your answer from above, and it probably actually does require a bit of understanding of continuous random variables and median, etc. So probably part C, B and C, B part 1 and part 2 are a bit beyond the scope of 2020, but you should be able to do part A, and I would encourage you to do that. Okay, so x is a continuous random variable with a probability density function, so it's a piecewise function with a product of a linear and a log function between 0 and 1, and then 0 everywhere else. Part of the graph is f is shown below, so we're seeing the important part, which is really this. It's 0 everywhere else out here. The graph has a turning point at x equals 1 on e. Okay, so that's marked there. Show by differentiation that this particular expression is an antiderivative of this. Okay, so what this is telling us is the antiderivative of this thing gives us this thing, which means that what we want to show instead is that the derivative of this thing gives us this thing, and use that to then infer what we learn about the antiderivative. Okay, so we want to work out the derivative of x to the k over k squared times k log e of x minus 1. Now we're going to need a product rule. We're going to need the product rule whether we expand those brackets or not, because there'll still be a product of the x to the k times log e of x. So I'm just going to do it as a product rule here. So derivative of the first part of the function, which is this bit highlighted in yellow, and then the green bit is the second part of the function. Okay. So derivative of the first, we're not differentiating k squared. K is a constant, so this is just x to the power of a number divided by a number. So we know we're going to get k times x to the power of k plus 1. That's still over k squared, so that will simplify. We're going to multiply by k log e of x minus 1. And then we need to add, for our product rule, we'll leave x to the k on k squared, and we'll differentiate the bracket. Derivative of log e of x is 1 on x, so that becomes k on x, and derivative of 1 is 0, so we've just got k on x. Okay, let's tidy that up. So k is going to cancel here, so we're going to have x to the k plus 1 over k times k log e of x minus 1, plus, if we tidy up here, again, one of those k's will cancel and one of those x's will cancel. So we get x, so we've got x to the power of k divided by x to the power of 1. Subtracting those powers is x to the power of k minus 1 over k over x, k over k squared just leaves us with a k on the denominator. Okay, so that's quite nice because now that's actually the same as that. And if we expand out the bracket, we've got x to the power of k plus 1 on k. Sorry, expanding the bracket, the k is going to cancel. My apologies. The k here will cancel with the k here when I multiply that. So I'm going to get x to the k plus 1 times log e of x minus x to the k plus 1 over k. Okay, so that's that times the negative 1. And then outside of the bracket we've still got plus x times k minus 1. Sorry, that should be k minus 1 up there. Oh, what have I done here? Sorry, there should be k minus 1 when I differentiated. So, multiply by the power and then subtract 1 from the power. Sorry about that. K minus 1 on k. Okay, so now these are cancelling out, minus that and plus that, and so we've just got x to the k minus 1 times log e of x. Now we want to be clear about answering the question. So we wanted to show by differentiation. So we've done the differentiation, but we want to show that this thing is an antiderivative of this thing. Okay, so what we know at this point, so if the derivative of x to the k on k squared times k log e of x minus 1 is equal to x times k minus 1, x to the power of k minus 1 times log e of x, then that means that the antiderivative of x to the k minus 1 times log e of x with respect to x is x to the k on k squared times k log e of x minus 1 plus c, but it's an antiderivative, so don't worry about the plus c. Don't need to worry about the plus c. Okay, so that was possible in 2020. It's a differentiate this, hence anti-differentiate this essentially. The rest of this is going to be a bit tricky in 2020. However, if you're watching in 2021, this should be relevant to you. So calculate the probability that x is bigger than 1 on e. Okay, so we know that the probability of x being bigger than 1 on e is the integral from 1 on e to 1, okay, because that's, if we go back up to our graph, what we're actually trying to find here is this area here. That is the probability that x is bigger than 1 on e. So we're going to use an integral to do that, integral from 1 on e to 1 of our function, which was, sorry, where am I? Up the top here, sorry, this was our rule, negative 4x times log e of x. Okay, I might just take that negative 4 out there for a minute. So it's going to be 1 on e is 1 of x log e of x dx. Okay, so what we want to think about is how we can use what we learnt up here. So if what I'm trying to do is anti-differentiate x log e of x, that's what I want to be able to do, well that must mean that k is 2. Okay, and so therefore that's going to be, it's going to be this when k is equal to 2. Okay, so it's going to be x squared on 4 times 2 log e of x minus 1. Okay, so we want to use that. So this is going to be, still got that negative 4 out there. Sorry, so it's x squared on 4, 2 times log e of x, take away 1. And we're doing that between 1 on e and 1. Okay, so before I do that, I'm going to put that 4 back in because it's going to cancel nicely with that fraction. So we're just going to have negative x squared times, times 2 log e of x, take away 1, between 1 and 1 on e. Sorry, I've I should have predicted my space a bit better here. Let me just make that a bit smaller. Just move it over as well. Okay, so we have got, we're going to substitute in 1, so that's going to give us negative 1. Actually, I might just expand it out first. So that's going to give us positive x squared take away 2x squared log e of x. And we're doing that from 1 on e to 1. Okay, so that is going to give us, subbing in 1, so we're going to get 1 minus 2 log e of 1. And log e of 1 is 0. And then we're going to have 1 on e squared minus, so it's just going to be 1 on e squared, minus, it'll be 2 on e squared times log e of 1 on e. Okay, so this is 1 minus 0, that first bracket. So then we've got minus 1 on e squared, and then plus 2 on e squared times log e of, now 1 on e is e to the negative 1, and the advantage of that is we can bring that negative down, and log e of e is 1. And so this is 1 minus 1 on e squared minus 2 on e squared times 1. Okay, so minus 1 on e squared, take away 2 on e squared is take away 3 on e squared. Okay, so that's the probability that x is bigger than or equal to 1 on e. Okay, so we want to use our what we've learnt above. So hence tells us we must use this. It would say hence or otherwise. If we can do it a different way, we must use what we've learnt up here to explain whether the median of x is greater than or less than 1 on e, given that e is bigger than 5 on 2. Okay, so what we know is we know that we've got this probability density function. This is 1 on E here. We've found that this area here, and hence the probability that x is bigger than 1 on E, is 1 minus 3 on E squared. Okay? So what we really want to know is, we know that the median is the halfway point. So we want to know, is this bigger than 0.5 or is this less than 0.5? That's what we want to be able to work out. And that's where they've given us a sort of suggestion that, well, e to the power of, e is bigger than 5 on 2. Okay. So let's have a think about what we know. So we know that the probability that x is bigger than 1 on E is equal to 1 minus 3 on E squared. Now, we can sub 5 on 2 into here, but I find that, personally, I think that's a harder logical step to work out, well, if I put 5 on 2 in here, is it bigger than or less than, and what's actually happening there? So I actually think it's a bit easier. It takes a few more steps, but I'm a bit more sure of what I'm doing if I do some rearrangement here. So this is 3 on E squared is the same as 1 minus probability that x is bigger than 1 on E. And so then that is going to be E squared is equal to 3 over 1 minus the probability that x is bigger than 1 on E. Now I know that E squared has to be bigger than 25 on 4. Okay, and so therefore, if E squared has to be bigger than 25 on 4, and this is equal to E squared, this has to be bigger than 25 on 4. Okay, and so now we can manipulate this. I'm going to multiply by 4 and divide by 25, which is going to give me 12 on 25, and I'm going to multiply by 1 minus the probability of x bigger than 1 on E. Now, just being a bit careful about your inequalities. We know when we multiply or divide an inequality by a negative number, we have to reverse the sign, but probability of x being bigger than 1 on E, that's a number between 0 and 1, and so therefore 1 minus that is still a positive number, so we multiply by that, it's still positive, and obviously multiplying by, or dividing by 25 on 4, 25 on 4 is positive as well. Okay, so what have we got here? If I, that's the same as if I add the probability that x is bigger than 1 on E to both sides, and subtract 12 on 25 from both sides, I get this. And so I learn that the probability that x is bigger than 1 on E is bigger than 13 on 25. Okay. And so therefore, I know that this black area in here is bigger than 13 on 25, which is bigger than half. And so therefore, if that bit of the area is a half, the median is going to have to be bigger than 1 on E. Okay, so the probability of x being bigger than 1 on E, probability that x is bigger than 1 on E is bigger than 1 half, and so therefore, and 1 half is what the median is, and so therefore the probability that x is bigger than 1 on E is bigger than the probability that x is bigger than the median, and so therefore the median must be bigger than 1 on E. Let's just be clear about what it wanted to ask, hence explain whether the median of x is greater than or less than 1 on E. So let's just be clear about the fact we're talking about the median of x is bigger than 1 on E. Okay. The diagram helps to support your argument, especially where you're being asked to explain something. Okay, so don't be afraid of including a diagram. It's clear. We can see that up here as well. Okay. All right, and that is the end of the 2016 Exam 1. So I've completed that. This video recording is just over an hour. So given that you're not actually explaining you're working to anyone as you're completing the exam, completing this paper within an hour should be feasible, hopefully. The last thing I would say is please make sure that when you complete each VCAA exam, you take the time to go and read properly through the examiner's report. As I've said previously to my own class, that the information in the examiner's report is really vital. There's a lot of things in that they say every year, and I know that might mean you think, oh, that's tedious, they said that last year. But the point is that those are errors that students make every year, okay? Don't make the mistake of making them again. The students in 2016 made all sorts of mistakes. The examiner's report highlights and corrects those mistakes. You want to learn from that so that you don't make those same mistakes as well when you do the 2017, 2018, or when you actually sit down to do your paper this year.